Now we begin the animation and discuss our design process for each step. We chose two separate deep groove ball bearings resting on either side of the output gear with no bearings on the input shaft. Deep groove ball bearings allow for the radial load as well as a small thrust load and are relatively inexpensive. We chose bearings with a bore size of 5/16 with an outside diameter of 15/16. We followed the specification that total reliability of the bearing must be 99.99%. We chose 1.3 as the application factor to account for environmental factors. We chose a shielded bearing to limit dust penetration into the gear housing, and this bearing is commercially available from SKF with a C10 value of 877 pounds. The design C10 for both bearings is well below this number. Our team designed a shaft with a thickness of 5/16 and a length of 2.5 inches. We assumed a maximum of 5 pounds force acting axially and a calculated value of 5.33 pounds acting radially and tangentially at the blade. The critical section is where the largest stress is located on the shaft. We found this critical point on the shaft located at the bearing closest to the blade itself at 1 3/8 inches from the blade center. The slopes and deflections for the bearings and gears are within specifications. For the non-crown gear, the shaft slope at the gear location on the input shaft is less than 0.0005 radians, which is below the maximum. The slope at both bearing sites is below the maximum of 0.003 radians. We chose 1020 cold drawn steel for the material as it is readily available and inexpensive. We used merit factors of 1 for the load, temperature, size, and environment. K surface was calculated to be 0.883 and K reliability to 0.702. Using this information, we calculated a fatigue life of 94 million cycles. Along the input shaft, the first bearing will be press fit up against the housing, followed by the gear, then followed by the second press fit bearing. This process is to ensure that there is no axial motion.
Our team decided to use a one-stage 5:1 gear ratio step-down spur gear train. The input speed will be approximately 10,000 RPMs, and we assumed a transferred torque of 10 inch-pounds and a lifetime of 10 million cycles was used in the calculations. We decided for the application noise wasn't the most important factor because the noise generated at the specified RPM is probably negligible when compared to the noise of the cutting blade against the plaster cast. Also, spur gears are significantly cheaper, which helps to achieve our ultimate goal of cost effectiveness. To fasten the gears to the output shaft, we will be using a set screw, which is already designed into the hub on the chosen commercially available gear. We decided against a keyway because of the small diameter of the shaft. The commercially available gear from Boston Gear was aluminum with a bore size of 1/4 inch that will be bored out to the shaft diameter of 5/16. This machining operation is justified because the gears were inexpensive. Our housing is comprised of 3 separate sections. The motor housing is attached to 2 pieces used as a gear train housing. The first piece of gear train housing is connected to the motor housing by 4 grade 2 number 1032 socket head cap screws in a rectangular pattern. The second piece of gear train housing is used as an end cap to enclose the gear train. This housing piece is also connected with 4 grade 2 number 1032 socket head cap screws along the rim of the housing. All 8 of the bolts were selected to be the same bolt to reduce costs, so they are all 3/4 of an inch in length, with the grip running the full length of the bolt. This was necessary since the bolt is threaded into the housing itself. The manufacturer suggests a torque of 31 inch-pounds. Our team decided that gaskets would not be necessary because we are not concerned about any liquids entering the gear train housing. Basically, we felt that the environmental concerns did not warrant the added material costs and engineering expense of adding a gasket. With all of the housing completed, our team left 1/10 of an inch between a gear hub and the external housing. We felt that this minimum clearance was acceptable at this point because this is where a bearing is press fit into the housing. Therefore, neither the gear nor the housing should be able to move because there is no external load. Also, the gear is attached to the shaft by a set screw, which will be able to absorb a small amount of external axial load to prevent movement. Other than this point, the next smallest gap is 15/100 of an inch between the gear and the external housing. This level of precision does not increase overall cost, and the housing is not oversized.